So hello everybody, today we have come to the last lecture on the course of Embedded System Design, Verification and Test, and we are in the last part of the design as well as today we are in the last lecture of this course. So throughout a long journey we have covered all the basics about design, then we have studied about verification, and finally we have learned lots about testing of embedded system. Today basically in the last lecture we are going to cover a very futuristic topic, and in fact in this part in this paradigm very little work has been done, and in fact there is a lot of research challenges and open problems that exist in this part, which we call is the interaction testing between hardware and software. So from the term itself it seems that there is a hardware paradigm, there is a software paradigm, how you can integrate and test. So in this lecture, rather going into any particular solution, we'll try to look at the problem, what are the issues, and how tentatively people are trying to solve, and even if people are trying to solve the problem, what is so challenging about it. So what is testing and what is the importance in embedded system? Basically, what is integration testing rather basically? So the traditional system on software basically is coding, compile, assembling, link and execute. That is, normally you have a PC or your computing environment, you write a code and basically you see whether the code is proper or not, you do a lot of software verification and test on that, which already we have been covered by Professor Deka when we were discussing on the verification. But what is the special challenge in embedded system? So the problem mainly is the hardware platform is not available in the embedded system directly, right? If it's a normal computing system, I have a laptop like this, I can write my code and I know that the laptop hardware or the computing hardware is not having any faults. So if there is any problem etc., it is mainly with my software. So basically I can do a lot of verification of the software like black box testing, white box testing and fault coverage analysis and so many stuff which already we have discussed at length in the module in the second part of the course. But in embedded system the special challenge is the laptop given to me is not yet ready, or they say that a similar version of hardware will be available to you which will be very much application specific, because embedded system is totally application specific, and in fact the hardware may not be available to you in the beginning. So it's a kind of a stuff that two people have started the journey, or it's making a tunnel through two parts of the hill. So one tunnel will come from this side, another tunnel will come from this side, and they should meet. That is what is integration testing, and in fact it's a very difficult problem that if there is slight mistake in any of the tunnel drilling problem, the two tunnels will pass and they will never meet in the end. And historically many such incidences have happened in the engineering of tunnel drilling. So very synonymous problem here also. A group of people will make the hardware, a group of people will write the software knowing that such a hardware will be available to me in future. So you can understand how difficult the problem is, and the hardware people will make a hardware understanding that there will be some code which will be available to me in some point down the line which has to work on my hardware. Now you can ask me the question that let me first make the hardware and then I can ask the software people to develop the software. If you do this, there will be longer time to market of the product and you will lose the market business. So you cannot do that. So both the teams will start drilling and finally they have to meet it. So that is actually the special problem of embedded system compared to any traditional system where the hardware is built a priori. So this is what is the idea. So basically what is having, we have a system definition, then we go for hardware software co-design, that is partition. There is a function design and then we partition what has to go in hardware and what we have to go in software. So there will be hardware design, there will be a software design, hardware is fabricated, there is a software code which is developed, and interestingly the hardware fabrication people have to think in mind that such a code will execute on my hardware. I have to design like that. The software people have to think in mind that such a hardware is available and the code should run. So you can understand the difficulty. Basically, so both of them have some picture in mind and they try to develop. Finally, hardware is tested on its own, as in the last third module which I have taught you. Software is tested and verified on its own methodology. Finally, they integrate and test. So practically speaking, this last phase, although it is very important, but practically before time to market, we have a very little time to put on that. And in fact it's a very difficult problem. So people have found that most of the bugs which still remains in the hardware and software paradigm are because of this lack of integration testing and available paradigm. Now you can ask me what I can able to do it. So basically, can I have something called a preliminary software? Can I have a preliminary hardware where I can do some kind of integrated test from the beginning? The answer is very difficult. Preliminary software still can be developed. You can say that okay, I'll write some basic blocks and maybe I'll write some software which will work for only a very few of the inputs. But how can you have a temporary hardware? So if you have a temporary hardware, at least with the advent of FPGAs and CPLD devices which we've discussed in the last lecture, slight research has been going on to this direction. That if there is a prototype device where I can download my hardware and then I can still give you a hardware platform to download the software and go for partial amount of integration testing. But still it is a very nascent stage, because as I told you, in a general purpose or in general sense, the hardware are quite involved, and you may require a lot of FPGAs to download a real hardware which has to be fabricated in ASIC. Because nowadays it's true that we have very large size FPGAs, but for many practical applications multiple FPGAs has to be used to design, which is equivalent to a single ASIC. Because as we have seen that FPGAs are basically some kind of general purpose hardware. So the difference between the advantage of FPGA is that you can very quickly have a prototype, but the area will be higher, and at speed testing cannot be done because FPGAs are generally slightly slower than your contemporary ASIC designs. But still some work has been done, or people are trying to emulate or they make a prototype hardware and download the software and try iterating, debug the bugs easier, so that when you read to the fab and software code, many of the design handshakes has been done. But again, it's a very, very challenging problem. So basically why all these problems happen? Because in the first class only I was telling you, when a technology matures, fault tend to decrease, a new technology evolves. Therefore, always the testing issue or verification issue comes into picture. Because if I have a fixed hardware which is very well tested, like in a normal computing platform, like a server, like the laptop which is already well tested. So if I write a software on this, then I can concentrate on debugging my software. But in embedded system, it is always going to cutting-edge technology. So always we target that a new processor or new embedded processor will be coming into picture, a new embedded hardware will come into picture. So my code should run on that. So in fact, that high-end hardware is not available to me as of yet. And for the hardware designers, neither the fabrication technology known a priori, neither the software which will run on it are known a priori. So basically, everything is very futuristic. Everybody has something in mind that the target they should meet, and they all are rushing towards something like to meet some goal for which the technology is not yet matured. So if you have such a futuristic goal and you are trying to match it, the problem is that you will tend to have a lot of bugs and you have a lot of faults which may be in place. But what is the solution? You have to debug, you have to go for integrated testing, and you have to maybe you can go for some kind of prototype development, preliminary level of test. But you cannot say that I will have a predetermined hardware and I'll write a code for that. If you do that, you will lack the market speed, because all your competitors are making a futuristic hardware assumption, writing the software. The hardware people are having a very futuristic software application in mind, writing the hardware for that, and finally they are going to meet. So you cannot lag behind anybody. So therefore, we should have a futuristic fault model into picture, we should have a prototyping device, and we should start aiming that something will be available down the line, and all our designs should be targeted towards that. So this is unlike any traditional system where the basic technology is mature and well tested, resulting in very less number of faults or bugs. So in many of the cases, the hardware platforms are mostly well established. Like in a traditional software development, the hardware platform is well known. Only the bugs are discovered in the software. But in hardware, nothing is available, everything is in the air. So the target hardware, target software, both are developing, finally they should meet. And therefore, there are a lot of bugs which can be found out when you are going for an integrated test. But still, this is the need of the hour. So you should have very good technologies to go for this integrated test. We should start from the beginning of the design. Not basically, we should not target here. We should rather target something like where we can do our prototype design verification much before the final phase, like something like this. So basically, it is some kind of a hardware, this is current model of hardware software co-design. So you have concepts, software analysis, hardware requirement analysis. So basically this is your hardware development. So you see, you partition into hardware, then you have requirement analysis, preliminary design, detailed design, fabrication, and finally the hardware test. Software means what part you are going to put in software, software design analysis, preliminary design, detailed design, unit coding, integrated testing, black box testing, white box testing. Finally we have the code, and finally we integrate and we are going to do it. So you see that this final level of test is only towards the end, which makes our life very, very problematic. So what is the problem? System immediately partitioned into hardware and software. After some time down the line, you might have found it, okay, this part I should have moved in software, or this part of the software I could have moved in hardware, then I would have been a better design. Very difficult to go in this straight flow of design. There is no iteration back. If you see, I do not have any iteration back, that from some part I can again change the hardware software partitioning. That people do not do, because the partition, then two teams start doing their job. Interchanging hands is a very, very difficult problem there. So that is one of the main issues. Then hardware and software are developed separately. Hardware first approach is often adopted. That is what I am saying, but still it is not very good. That is, you first fabricate the hardware, targeting that software will come and execute it with me, and then you employ the software and see everything is there. But it will make this is actually a practicality, even if many of the industries may tell you that we are having co-development phase and all, but still it is practical, but still it hits the market. Because if you make a hardware and the software team starts the job later, then you can find out that we will lose time to market. So it is always people try to do it parallelly, but still for the many of the practical applications, hardware are developed first and tested, software is downloaded and seen whether, with the assumption that the hardware paradigm is correct, which is in most of the normal computing platforms, they follow this approach, hardware first. But for embedded system industry, practically many of the industries follow hardware first approach, but this will lead to a situation when you will be quite behind in others market. Like the story I always tell you about Nokia and some other phones like Samsung. So I mean, this is just some example, should not go about the exact vendor, and for just an example I am telling you, this is nothing to do with favoring Nokia or Samsung in general, but the idea is that Nokia was to give a very nice robust mobile phones. Samsung on the other hand started giving lot of features, but initially they had much more bugs or robustness compared to a Nokia. But who won the market? Samsung with the smartphones. Why? Because they were having futuristic development ideas, that this is my hardware available, this is the GUI development. So all started in parallel and finally they met. But if you do such an approach, then it's true that there will be some bugs and phone might have some problems. But Nokia was following the hardware full verification kind of a method, so that all their phones were very, very robust and there were very less bugs. But still, who won the market? Who could give more features with little amount of bugs? Because with a handheld device, generally for home usage or non-critical usage, so with slight bugs I can tolerate the design, but I need lot of features. So that is the idea of embedded systems. If this is slightly different from mission critical applications, where we have to be super sure that everything is operating fine, but 99% of the embedded systems are basically for homemade or home devices or for personal and non-critical uses. So the market is very, very high there. Your microwave and washing machine, mobile phones, everything basically is an embedded system nowadays. So therefore people try to go for a parallel approach and try to see basically how much features they can give. In that case, the integrated testing and integrated development environment becomes very, very important. Another problem is hardware software trade-offs are restricted. As I told you, this is hardware, this is software. If down the line I find this should be put in hardware, this should be put in software, such chances are not available to us. So that is the problem, that trade-offs are decided in the beginning and in middle you cannot have a handshake. Problems are poor quality design, costly modifications, schedule slippages. That schedule slippage means I cannot meet the target. I was saying that this hardware would be available, then my software would run. Hardware people have taken more amount of time. So such type of stuff happens. So we require co-development and co-integration and co-testing phases of hardware and software in embedded systems. But again, as I told you, it's a very, very difficult problem. So there are some incorrect assumptions in the current design process. Hardware and software can be acquired separately and independently with success and easy integration in the two later. That is what people have thought, that I will make a hardware with the assumption this exactly the hardware will work. When I am making the hardware, I should have a knowledge that exactly the software would work, and finally they should integrate fine. But that never happened basically. Hardware problems can be fixed with simple software modifications. These are some practical things which people have faced. So people thought that, okay, if the hardware has some bugs, then I can write the software with slight modification that these bugs become maskable. Right? They are not faults, right? Bugs basically. So, and people also thought that because software can be modified, hardware cannot be. So the hardware people are thinking that such a software will be available and I am going to do it. But in the end, hardware had some bugs, not faults, design errors, because the software is not available with them. So they cannot directly verify the hardware exactly that how it would perform when the software is executed. So that's a problem. So people generally thought that we have a hardware and we write the software. If there are bugs in the software, we'll try to hide them. And in fact, many processors or many embedded hardwares had software bugs. The software was slightly tweaked or operating systems were slightly tweaked so that the faults become marks that you do not feel the effect. So even no industry will tell you these stories because that will put a very bad mark on them, but that is the truth. So once operational, software rarely needs modification or maintenance. That is also not true basically. That is not basically too much relevant for embedded system. What people thought is that the hardware is there, you dump the software, then your job is done. But in fact it is not. We require quite updation of the softwares because on the same hardware paradigm you can also improve the versions of the software. So your hardware should not only target that this is the software that would be downloaded, you should be slightly futuristic. Like I have a mobile phone and I download a version 1 of the embedded OS. After sometimes I'll download some applications. Then I'll also update my OS of the hardware frequently. Your hardware should be able to support that. So previously embedded people thought that this is the hardware developed for this target software. After that there will be no renovation on the hardware. Is simple because hardware cannot be renovated, software will also not be enhanced. But that was not true. So if your phone or your handheld device do not allow enhancement of the software is a very mad marketing or design policy. So your hardware should also be futuristic. Not only it will be able to download this operating system and operate with it, but you should also see that it should be able to work on version 1, 2 and 3 and so forth. So this brings lot of hardware design challenges, okay? And right, so this is basically some of the assumptions which were not true in the embedded domain. So basically hardware software cannot be designed so easily separately. Integration is a very big challenge. Hardware problems can be solved with software, from that is true, but with very modern paradigm it is very difficult that all hardware problems can be masked with software. Secondly, like some part of the hardware has a problem, so maybe we will not try to access those parts. There may become some redundant parts, we will only access them, something like that, okay? So again, basically software rarely needs modification in embedded systems. Not true. Basically because hardware is fixed, software is fixed in embedded system. Generally it was understood, but in fact hardware cannot be changed, but lot of updated versions has to be downloaded and executed. So you can understand the problem. This is extremely challenging problem to design a pure new embedded system with lot of guarantee of success, lot of trade-offs to be given, because two people are starting there. If in between something you find that this has to be changed to hardware from software, this can be mapped from software to hardware, but I am not able to provide that because we are called in unidirectional way. Integration, you may find lot of bugs. In that case people cannot modify the hardware, they will try to tweak the hardware and do it. So you can understand that if I can somehow make a co-development environment, then all my problems will be solved. So that is what is shown in this slide. So integrated modeling substrate. So we require a part which can model your hardware as well as your software. Software modeling is very simple. It's any just programming language that is the model of the software. And if you want to go for a preliminary design, you can go for block level design. Then you can slightly make it more. You can enrich these blocks with code and so forth. And simulating a software is very simple. Main problem is with this software part. The software part is very difficult. Sorry, hardware. The software part is very simple. Actually, the hardware part is where the problem is. Because I can have a hardware in simulation, which I call a Verilog simulation, or all the models which Arnab sir has told you. But they are all at the hardware level. One level is hardware simulators, one level is software simulators. Software simulators are like C language, Java, whatever programming language you are using, compilers are using, you can tell them that is the software simulator. There is nothing that executes your software. But when I am talking about hardware, the hardware is not available. Only I have the software representation of the hardware, and the software compilers like HDL, Verilog compiler, VHDL compilers, they will take the Verilog or VHDL code which is representing the hardware, and then they will try to tell you that this is how the software will behave. But we rarely have some kind of a simulators in which case you can put the software in the hardware which is also in the software version. Like this is hardware, pure hardware, but we do not have that. Verilog, VHDL, all are software representation or software models of the hardware. And we have some C code or Java code which I am going to execute on this hardware. So these hardware simulators, this is a pure hardware. We have some hardware models which are running in this software like Verilog VHDL. So if I say that VHDL, so this VHDL basically models this hardware which is written in a soft language. But VHDL cannot simulate this hardware with this C language. Those things are now not available, or not, even if it is there, they take long time to simulate. The idea is that I have written a Verilog code for an adder. So it is there. The code will simulate and tell you how the hardware will behave. But if there is a C program which will access this adder, the Verilog simulator cannot simulate that. Because Verilog simulator will simulate the hardware which is written in Verilog or VHDL. But if a C program runs on top of that, how that C program will be executed on that hardware, there are very difficult, such simulators are very difficult to develop. Even if it is developed, it is very slow, which actually takes the hardware represented in Verilog or HDL, there is a hardware is represented in a hardware definition language. On top of it, there is a C language program or some language program which is running on that, and totally on entirety it is simulated on your some kind of a platform. So if that is available, then our problem is solved. So some simulators are available. It's not that simulators are not available, but it will take a long time to simulate a large or a practical design, because it has to simulate the software, it has to simulate the hardware, and how they are integrated, that has to be simulated, and everything is done in the software paradigm. So it's something like one hardware on top, one processor is there, on top of that you are putting another sandbox, on top of that you are putting another sandbox, and you are running multiple operating system on top of one another. So one OS is simulating another OS is simulating another OS, and it makes things very slow. I'm just giving an analogy. But here the hierarchy is C language, on top of it is a hardware hardware, but it's not exactly hardware, it is a hardware written in Verilog and HDL, and entirety there should be a simulator which can take the hardware in VHDL and C language which is running on that VHDL version of the hardware and total how it behaves. Very, very difficult to get something like that. So requirement for an ideal co-design environment: unified, unbiased hardware software representation. So you can represent in a single environment both the hardware as well as the program. Supports uniform design and analysis techniques for hardware and software. Permit system evolution in an integrated design environment. Allows easy migration of tasks either into hardware and software. So if I can give you an environment where I can write the hardware in Verilog or VHDL, I can write the C program which has to be running on that hardware, same environment I can code, and the simulator what it will do, it will take the C language or whatever language you have written the soft code, will take each instruction of that, map it onto the hardware which is still in a soft language like Verilog and VHDL, and finally it will tell you how the hardware will behave when such instructions are taken into picture. So that is actually called unified or co-simulation environment. That is much challenge to design. In fact, it's much challenging to design a very fast working simulator on that. So if it is there, then you can allow different tests like this part in hardware, this part in software, how it will behave. So basically you can find out if there are bugs, at what point the bugs is. I think it's very obvious that if I have an entire simulation environment from the beginning, a single team or people are working in very close hand in hand to find out whether how the system is behaving, if this part is hardware, this part is software, if the bug, whether the bug is in part A or part B, or is it in hardware or in the software. So in fact, is an entire software given to you, a part is for the hardware, a part is for the software, together you are simulating it and it becomes a co-development environment, co-debugging environment, and life becomes very easy. But the problem is making such a simulator is difficult, as well as it will become terribly slow to simulate practical designs. Right? So that is what is required. Integrated modeling substrate. Supports evaluation at several stages of the design, supports stepwise development and integration of hardware and software, as I was telling you. Validation ensures that the system implemented meets the initial system and final system requirements. So basically it ensures that the entire system to be finally designed will meet the initial system requirement. So initial system requirement, as you see, is not partitioned into hardware and software. It's the initial requirement. Now you have now if you look at it, what it says is very interesting. So if you look, this is a system requirement. Right? This part is in hardware and this part in software. So if you take the traditional way, the whole system concept can again be tested only in the end. When the practical hardware is there, you can test it. But here the idea will be basically you have an integrated modeling software. So at each point of time, basically you can validate the entire system specification, which is not possible in the traditional design flow. So that is actually called cross-fertilization between hardware and software. So basically what I was telling you is basically is written in this slide, that mainly we should have a co-design environment. That is very important. It's cross-fertilization. We should have a hardware representation as simulation, we should have a software representation as a simulator. Both should be able to integrate it at the simulation environment, and then you should be able to see the results. This will allow you to develop test codes much before. This will allow you to find bugs whether in the hardware and software in the beforehand. They can allow you easy trade-off between the two, so that you get a very, very nice embedded system design environment. There are lot of designs available, right? Environments available to do it, but they are all at a very what I can say a theoretical level, or even if the cross hybrid environments are there at the simulation level also, they are very less in numbers, and the main drawback is the speed. And then that's I'm just going to show you a very, very simple example why it is challenging to build such a simulator. Like for example, let me zoom this code for you. A simple code. What it says, input n, output s equal to 0, for I equal to 1 to n, s equal to s plus 1. What it does, it iterates and add s equal to 0, 1, 2, 3, 4, 5, 6, 7, 8 up to n. That's it. So this is a simple software. But if I write as a hardware for this, if it's a C representation, you can understand it's a class 12 exercise or just VTech first year exercise. But if I write it in terms of very long, what is the representation? Extremely, extremely difficult. So this is basically the hardware implementation for the the register transfer implementation for this. So what we will have, you will have an adder. Fine. You should have a counter. So initially the counter will be loaded with n. Then there should be a comparator, because every time it's a down count. So every time it will become n minus 1 up to 0. So whenever there is a comparator, it will be comparing with 0. So whenever it is 0, it will freeze the value. That is going to freeze this one. And initially this sum will be reset to 0. So there should be a reset line which will reset it to 0. Right? Then basically this counter will have the value n. So in the first time, initially it is loaded with n. Then basically this is reset to 0, and basically this comparator has a value 0. So at present 0 and n are uncomparable. So now this is a freeze line. So this is not freezed basically. So what happens? So you will have 0 plus n is equal to, now it will be n. So it will keep on, then it will be becoming down counter n minus 1. So sum will be equal to n minus n, n minus 1, n minus 2 and so forth. So this is a simple RTL design. I am not going into the VLSI design as present, but I am just trying to give you an idea that why it is very difficult to make a co-simulation environment. And it decrements, finally becomes 0. So when it becomes 0, it will make this this tri-state as high. So whatever value is in this sum register will be coming out over here. That means now 0, 1 from n to 0 it has come, the counter has come, started from n coming to 0. So at that time the tri-state is enabled. So whatever value is basically retaining over here is coming out, and it is also freezing this sum register. It will no more increment or decrement or do any addition. So this is a simple typical circuit. So basically this is the Verilog representation. So you say always at the passage of clock, if reset, out is equal to 0, count equal to in, count equal to in means it will be loaded with the value n, and ready bit is set as 1, some variables you have set. Then if the reset is not there, if count is equal to 0, ready bit equal to 1. Count is equal to 0 means the counter has been set, so you make the ready bit equal to 1. Ready bit means it will be freezing and sending the value to the tri-state. Else out equal to out plus 1, count equal to count minus 1. So you can see there is a clock edge, there are registers, there is a initialization code, there is basically a incrementing code and so forth. So basically this is a Verilog representation, and finally this is your, it will be synthesized as a hardware like this and so forth. So what I try to mean by this, I am not going to teach you, I am not teaching Verilog or so hardware design in this slides. I am telling you, see the difference. So this is the software and this is basically the hardware representation for a same design intent. So such difference in the hardware and software description. So it is very, very difficult to make a uniform coding environment or uniform simulation environment. True, but still people have overcome this. Lot of theories has been developed. As I told you, these are very, very futuristic research problem, and people have really tried to develop environments where even if it's a hardware or software, still how they can be simulated together. Just this was just to motivate the challenge that why it is difficult to have such a different co-simulation environment, right? So that is what is very, very important. So if I somehow can do it, then what is the idea? So if I can somehow have a unified software hardware representation, so a representation of that system can be used to describe its functionality independent of its implementation in hardware and software. Initially you have a very integrated environment. Then you can software partitioning, you can delay till a long time, that okay, I am trying to, this is an integrated environment, I am trying to go right, and till when I am going in the final stage, then you can have a more clearer picture that which should go in hardware and which can go in software, because I have an integrated environment. So I can try all this, and towards the end, when more or less all the design components are clear, I can do a partitioning which will give me a better control for efficiency, right? So that supports cross fertilization between hardware and software, provides a simulation environment after partitioning is done. So that means in a nutshell, if such an environment is available to you, most of your embedded system solutions problems are solved. Problem number 1, what is solved? The problem number 1 is very simple. That is, I have a co-environment. So whatever hardware, software version I have, I will download, and I should they give the simulate and see whether there are anywhere bugs or not. So bugs will be developed very early. I can also find out that at every stage the design is correct or not, because I have an entire working version in software. So I can see whether the design intent is made. Bugs are caught earlier. Easy design trade-off. That I find this one is good in software, I can put it in hardware and vice versa. And also it is said that I can delay the partitioning. That I can have an initial big model, and then I can go quick iteration. Still, when I have a more or less a complete system idea in my mind, then I can find out, okay, this I put in hardware, this I can put in software. So this will actually give you a better debugging capability, better test capability, better solution efficiency and so forth. But only issue is that making such an environment. So that is actually, people call it called a virtual machine. So basically what we can have is a virtual machine is some kind of a machine which will emulate or simulate your hardware. This is a software. It will run on a hardware. So basically the software layer is very close to the hardware, that hides the hardware details and provides an abstract view of the to the X programmer. That when I am writing a C code, I need not think about the hardware. But in case of embedded system, the software person has to think of the hardware. That is what is the problem. So if I can have a virtual machine, or if I can somehow emulate the hardware on which the software will run, our job is solved. So basically all the co-simulation environments work on that. The hardware is written by a hardware person in Verilog, but the co-simulation environment basically abstract out the hardware part from the software part. So the software developer will find that the hardware is already there in place, which can execute its software. Of course, the hardware will also be developed in phases. Initially, it will have block diagrams, so that you can do just functional simulation maybe. After that they will implement a register transfer level. Then you can also put delays and you can find more detailed analysis of your hardware. Finally they will simulate the gate level design. So in that case you can have exact delays, you can have abstract latch problems, you can find out how many power it is taking and so forth. So it's a hierarchical solution. First you have just the functional implementation, then you can have delay implementation, then you can have power implementation, and all these parameters will slowly come into picture. But the idea is that at every point of time you have an entire simulation of your entire system. That is the key goal. In traditional design you have a hardware version, hardware partition, software partition. You cannot simulate the entire solution. Only when the hardware has been fabricated and come, then you can put it in the software in that, and you can get the working version of your entire system. But here it is the other way around. From the starting only you will having a simulation environment of your design, but maybe at a very abstract level in the beginning. Then after some time you will put more details onto the design, so you can get more features out of it, or more test characteristics, or more more insight you can get about the design. Like I can have a black box software and I can have a very high level architecture design at block level, at the RTL level. Then I go for gate level. Then when I am going to gate level, I can find out the delays, I can model the delays in a better way, I can know very well what will be the frequency of my circuit, I can also have a power model, so I can get more insights on the design. But at every point of time I have a simulation level. So I do not need to wait till the end to find out the bugs and land up in surprises. That is what is basically the idea, right? So we should always have some kind of this abstract. So this is the current abstraction mechanism for software system. Basically this is what is currently being done. So they have a hardware emulation or hardware software virtual machine for running the hardware, right? This is what basically is the abstract hardware software model. So you have an abstract hardware software model. So there is general purpose evolution. It can support so many things, but this is what is basically your challenge, that how can you have a simulatable or emulatable abstract hardware model. That is what is basically the challenge. So you can do lot of general purpose system evolution, you can do evolution of design alternatives, you can do evolution of software hardware trade-offs, identification of bottlenecks or bugs. Everything is possible, but I require a simulation version of this, which is the main challenge. So how people have tried to do it? They have something called a Verilog hardware simulator. In this case you can download your hardware first maybe at RTL level, then you can go basically at the gate level, and maybe at the very detailed level. So you can do a phase wise. So this is your hardware, this is the hardware which simulates the Verilog. And you have some software procedures. But as I told you, Verilog can only simulate your hardware. It cannot simulate the software on top of that. But people sometimes also put some kind of a interfaces. They have written some kind of interfaces, that is the software environment, co-development environment. People have written a lot of interfaces in the Verilog itself. So in that case what happens, it will take the software, it will convert this into some kind of a hardware representation so that they can be integrated with this environment. Again, making the story from the beginning, Verilog can simulate hardware which is written in software in languages like Verilog, or there are a lot of HDL simulators. So HDL simulators will take the soft version of your hardware and it can execute it, but it cannot take how a software will run on it. That they cannot do. For that, people have written some kind of what is called a BUS interface. They call it wrappers. That is Verilog PLI programming language interface, as they call it, PLIs. In that case, this is a hardware which is written in Verilog. You write some kind of wrappers. So in this, what the wrapper will do, the wrapper will take the software which is written in C, C++ or whatever language you want your software to be. It will translate those softwares into a Verilog representation so that they can integrate with the HDL representation of the hardware. Maybe this is some kind of a maybe simple, like it can be a simple adder which is written in basically your Verilog. Now this is a software which is using this adder. So what this PLI will do, this basically will translate this code of the C language which uses the adder so that it can fit into this, into the hardware environment simulator for this Verilog code. That is what is basically the idea. So it's an integrated environment. So again, such an environment can be developed, and there are a lot of web environments there, but the main problem is the speed. So it is actually, you can think this, it has become very complex. Hardware is generally some maybe 100 lines of Verilog code makes a hardware. Now if you are trying to integrate with the C, so C language will be taken, it will be translated into Verilog or mapped into a corresponding Verilog language so that it can interface with the hardware which is written by the Verilog, that is the pure hardware. So this software cannot, C language cannot be run on that in simulation, so they are converting into a hardware language which is compatible. So that code actually becomes very, very high, because C codes or software programs are generally very long in length compared to the hardware counterpart. Because hardware represents a hardware block or hardware definition language represents the hardware in software language. So those codes are generally not very long because it has to be optimized, because I find it has to be fabricated. So generally there are a lot of optimization techniques that goes in. But software codes are generally implemented general purpose functionality. So if you are representing general purpose functionality using a code, generally it becomes very, very long. So if I try to represent such C codes using its Verilog representation, the code becomes very, very large and complicated, and the simulation takes lots of time. So what is the solution? People try to use this and dump it into FPGA. So it becomes a hardware representation. That is a real hardware. I don't require to simulate anything. This is called emulation. Then now you can directly download your software and you can test it. So nowadays people are actually taking this environment. So that is why FPGAs have become a very, very key role player in integrated environment based test. Instead of simulating the hardware, they write the hardware, develop the hardware fully, but I cannot fabricate it because it takes long time. You download it to the FPGA, and basically you download your software onto the FPGA, which is called emulation, not a simulation, and then basically you can see whether everything works. Still, it's good, but not as best as a co-simulation environment. Co-simulation environment is very flexible. You do not require any hardware. Everything is in software. You just write a code and see whether everything is proper or not. But as I told you, we require very high-speed computers to make a time-optimized simulators for such a co-simulation environment. So many people are trying to go in the other direction, in which case programmable devices are available. You download your hardware there, it becomes a prototype device, and you test your software. So with this, we basically come to the end of this course as well as this lecture. So this is a very open problem. So verification, test. So main problem comes because we do not have the full design at hand. Because when I talk about embedded systems, you partition it, something into hardware and something into software, and you test it separately. It's very challenging to develop an integrated environment and to solve the problem. So that is one of the key challenges where all embedded system people are working for. So it is an open problem. Like, so you have to look at mission critical systems, you have to look at for handheld devices, you have to see for personal devices, and I require a common modeling environment, common verification environment, and finally common hardware development and test environment. Can I do it in a single window? That is what is the key role, which is the open problem. So with this, we come to the end of the course. I think you have enjoyed the course throughout the last 3 months basically, and in fact also we should try to emphasize that this course, as was a part which included 3 different aspects like design, verification and test, we have tried to give you the some basic broad lines of all the different paradigms. So this becomes a course in entirety. Otherwise we have not gone into too much details of each of these steps because they would merit a course in itself. But we thought that basically this course should be a first course towards embedded system in entirety. Because when I am putting these 3 phases together, because no embedded system can be complete with the design phase alone or test phase alone or verification phase alone. Entire embedded system design flow comprises of the design, modeling, verification and test. So that was our emphasis. So with this, we would like to thank you all for your patience listening over the 3-4 months, and all the best for your exams. Thank you.